So now we're at our final example for the non-mutating algorithms, and this one's going to illustrate some interesting examples that make some assumptions about the range that they're working on. And in particular, they assume that the range is going to be ordered. And we're going to demonstrate the use of a couple of different algorithms for doing binary search-like capabilities. So as before, we're going to have now is the time for all good people to come to the aid of their party and to find all good people. And you'll see why we have those variants of this. You'll notice also that I store these in built-in arrays. So I have an array of strings, now is the time for all good people, and string B, which is an array of strings to find all good people. So I start out by taking my array of strings, now is the time for all good people, and I sort it using our good old sort algorithm. So I end up with a sorted array. It'll sort it in place. And then I go through every word that's in array B. And for each word in array B, I go ahead and I search for the word using the binary search algorithm. And the binary search algorithm, surprise, surprise, does binary search. Now that, of course, has to assume that the range it's given is sorted, because otherwise binary search will have a flaming destructo mess. So it's going to go ahead and search from beginning to end, and it's looking for each word. Now, as you'll see, it'll find to all good people, but it won't find because, of course, find's not there. Now, the interesting thing about binary search, and I have absolutely no idea why they made such a ridiculous method, it only returns true or false. It doesn't tell you where the item was found if it found the item, which is really pretty pointless for lots of uses of searching. Usually when you search for something, you want to find it for some reason. But in this case, it just returns true or false. So that being wholly unsatisfying, we're then going to show an example of our own homebrew binary search algorithm, which I call binary find, which will tell you where the actual match occurred if there was one. So to show this, we're now going to make ourselves a vector of string, which will be given the beginning and end of the array of strings, which are sorted, so they're sorted. And then what we're going to do is we're going to go through and we're going to print out the contents so you can tell where every location, where every word appears in the vector. So we're going to print it out using a good old range-based for loop. And then what we're going to do is we're going to go through our array B, just like we did before. So we have array B to find all good people. And we're going to call the binary find algorithm. And that's going to return an iterator if there's a match. So if there's a match, then it won't be the end iterator. And we're going to say we found the word at a particular index. If there's no match, we also get an iterator back, of course, but in that case, it'll equal the end of the range. So let's go ahead and take a look. Well, let me run the program first so you can see what it does, and then we'll go ahead and take a look at binary find, because that's the interesting one. So you can see the first set of checks here, just found to, did not find, found all, found good, found people. No surprise there. Then we go ahead and take the sorted array and we print out its contents. So of course it's aid, all, come, for, good, is, now, of, party people, the, their, time, to. So that's sorted. And now we're going to go ahead and use the binary search algorithm called binary find that will tell you where the occurrence actually occurred. So here we went and we searched and we found 2 was at location 10. We searched, couldn't find, searched for all, that was at location 1, which is correct. We looked for good, that was location 4. Looked for people, that was location 9. So you can see people's at 9 and good is at 4. So that's not only telling us we got a match, it's telling us where we got the match. So let's go ahead and take a look at binary find. Binary find uses an algorithm called lower bound. And what it does is it does a comparison. So you can see here that we're going to pass in the value that we're searching for, and we're also passing in a comparison function. And what we're going to do in this case is it's going to do a lower bound. Now, when it gets a match back for this, what it gives you back is it gives you back an iterator to the item that is the first item that's not less than the item that we're searching for. But what we don't know at that point is whether or not what we found is going to be equal to the item we're looking for, or it's just going to be greater than the item we're searching for. So of course, in a binary search, we want to know, did we actually get a match or not? And the default behavior for this is to do less than. So if it comes back with a first, and if first equals last, we know we didn't find it at all. If first didn't equal last, then the question is, if we do a comparison, is that going to return true or false? If we do the comparison and it's less than, then we know we didn't find a match because it was the item that we are searching for is less than the item that came back. If we get a match, however, then we know that if we do not get a match, then we know that they're equal. We negate that. That makes that true. And so then we go ahead and return first because that says this is where we found the actual match. So lower bound is this kind of cool algorithm that'll tell you interesting things. It basically does a binary search-like mechanism, but to truly turn it into binary search, you have to do one more check at the end to see whether or not the item you got back was, how it relates to what you found. And if comparison doesn't, if the comparison functor returns false, then we know it matched because it's using less than. And if something is equal, then it's not less than. So that's the way to read that particular piece of code. So interesting example. I think it's nice to know that there's a way to make a binary search algorithm that's able to truly give you back some interesting, useful results and not just come back and say true or false, which doesn't seem very useful. So that's the end of our discussion of non-mutating algorithms in STL.